Thanks, Lars. Thanks, everybody, for coming. I'm going to tell you about white dwarfs, which have a lot of cool applications, even some multi-phase applications that apply to white dwarfs. These are some of the smallest stars in the sky, but some of the most exciting ones. They're the biggest thermonuclear bombs in the universe, and they have all kinds of interesting physics that applies especially to white dwarfs and not so much to other stars. So I'm going to get into some of those topics today. But just to start, just want to explain basically what a white dwarf is. So in a star like the Sun, you typically have hydrogen burning to helium at the center of the star. That usually happens very close to the center of the star. And then you have a bunch of hydrogen in the envelope surrounding the core. So what happens after you burn all the hydrogen to helium is, in a star like the Sun, you start burning helium into carbon and oxygen. So that's happening at the center of the star. And in a layer around that, you have hydrogen burning to helium. And in a layer around that, you just have inert hydrogen. So 99% of stars will basically get to this point. They'll burn all their helium into carbon and oxygen. And then that's all they can do. They aren't massive enough to reach the temperatures large enough to burn carbon and oxygen into heavier elements. So it turns out what happens is they expand into red giants, they blow off all their hydrogen, and basically all you're left with is the carbon and oxygen core at the center, which is a white dwarf. And as the star evolves, it has to keep contracting to get to high enough temperatures to burn these elements. And so you are left with this very small but extremely dense white dwarf at the end. I'll tell you what sets that density in a second, but it's usually about the size of the Earth, even though it has about the mass of the Sun. So density is about 1 million times larger than water. So I also want to say a little bit about why white dwarfs are especially interesting now, since most of the physics I'm going to tell you about is actually fairly old standard physics. But there's been some really exciting observations that are allowing us to then learn new things and expand upon the basic physical concepts. So one of the important developments is that it's gotten a lot easier to just find white dwarfs. It used to be kind of hard to find them. And the reason is, well, for one thing, they're small and dim, so we can't see them out to very far distances. What astronomers like to do is make things like brightness, temperature diagrams. So they plot stars on some axis like this, where we always have temperature increasing to the left, because astronomers do everything backwards. And what you could do is just plot the apparent brightness of a star. You could just look at all the stars. And if you just plot their apparent brightness versus temperature, you'd see just a big scatter plot. You'd see a lot of really dim stars down here. You'd see cool stars, hot stars. But basically, they'd be all over the place, and you couldn't interpret anything, right? And that's because some of these stars are near, some of them are far, some of them are bright, some of them are dim, right? So we know white dwarfs are dim, but if we look at a dim star down here, historically, it's been very hard to know whether it's dim because it's dim, like a white dwarf star, it's intrinsically dim, or if it's just a star that's far away, so it doesn't look very bright.
Which spectrum? Visible spectrum?
Yeah. So usually, most of these measurements are made in invisible light. You can also look in other wavelengths, and that can help you identify different types of stars as well. But those observations are often more challenging. So one of the things that's happened recently is the Gaia satellite launched several years ago, and that's now giving us distances to, 1 billion stars, something like that, which is orders of magnitude more than what we had before. And once you know the distance to a star, you now know its absolute brightness. And so when you plot stars as a function of absolute brightness, then you see very clear structure. So what you see is you see a main sequence of stars that get dimmer with cooler temperature. These are stars burning hydrogen into helium. You see red giants. Those are stars burning mostly helium into carbon and oxygen. And you see white dwarfs down here, which are dimmer than all the other stars. Yeah.
So how do you manage to get a distance?
So I didn't explain how the Gaia satellite works. Basically what it does is, because the Earth is orbiting around the sun, you see the positions of stars wobble slightly just due to the motion of the Earth around the sun. It's a very tiny wobble because the stars are much further away than the distance between the Earth and the sun, but that satellite can measure that slight displacement. And then you can calculate just from trigonometry how far away the star is. Yeah. So previously, how many stars did we have with Hipparcos? 1 million? Now we have 1 billion. So you can do a lot more. You can find 1,000 times as many white dwarfs as we used to be able to. So not only do we see the white dwarfs, but we actually see all kinds of little structure on this track. And that's a lot of what we're talking about. So we actually see a slight bifurcation of the track that corresponds to different compositions of the white dwarf surfaces. We see this little spur coming off the side that's been called the Q branch, which people are still debating exactly what causes that. So we're seeing all kinds of structure that we didn't know about before. Also, once you identify these white dwarfs, you can then take measurements with spectroscopes, polarization, all kinds of things to look for more interesting physics. So that's been one of the main developments. Also, similar ideas, other big developments in big data include just big surveys that just measure the brightness of 1 billion stars at a time. You can look for pulsating stars and eclipsing binary stars. Big spectroscopic surveys also allow us to find lots of white dwarfs. So these are all things, basically it's a big data revolution. To change its properties? Yeah, good question. So what a white dwarf typically does, it forms from a red giant. The outer layers come off and it forms very hot, right? Because it was just burning helium into carbon. So it forms very hot, but it basically has no nuclear energy source anymore. And so it just cools off and it just moves down this track to cooler and cooler temperatures. To get all the way down here, the coolest ones are basically the age of the universe. So they take 10 gig years to get down here. The ones at the hot end, they're much more rare because they cool through that area much faster. But typically those timescales are millions to billions of years. Yeah, it just depends. It's everything from basically millions of years to the age of the universe.
Looking at dynamics by looking up from here, other than you see different evolutions.
In most cases, and yeah, usually that's true with stellar astrophysics, but there are some exceptions. Okay, so let me tell you a little bit about what sets the size of a white dwarf. And basically, it's quantum mechanics. Okay, so probably an equation a lot of you remember from college, Heisenberg uncertainty principle. This is basically what sets the size of a white dwarf. Okay, the reason is that in a white dwarf, the atoms are packed very densely, so the size, delta x, between two atoms, actually specifically two electrons, gets very small. So delta x gets very small for electrons inside of a white dwarf, which means the uncertainty in their momentum has to be very large. So in other words, they start acquiring large momenta. Okay, so the typical momentum that they have is basically h bar over the typical spacing between electrons. So this is basically h bar times the number density of electrons to the 1/3 power. Okay, and the number density of electrons is basically just the mass density divided by basically all the mass is in protons, so it's roughly density divided by the mass of a proton. I'm dropping all the factors of pi and 2 and everything for this lecture. Okay, so you can then calculate the pressure exerted by these degenerate electrons. Okay, and the pressure is basically just number density times this momentum times the typical velocity. And velocity for non-relativistic electrons is just momentum divided by mass. So you can calculate the total pressure, which is basically h bar squared over mass of electron times density divided by mass of the proton to the 5/3. Or if I want to write this in terms of the typical mass and radius of a white dwarf, it's h bar squared mass to the 5/3, electron mass, proton mass to the 5/3, radius to the 5th. Okay, so that's the typical pressure exerted by electrons inside of a white dwarf. Now we can equate that to the pressure that you need to hold up the star, and then that lets you calculate the hydrostatic balance. And so that pressure is basically gm squared divided by r to the 4th, to order of magnitude. Okay, so we can just solve this equation, and we get that the mass, actually let me solve it in terms of radius. Okay, so we get that the radius of the white dwarf is roughly h bar squared over g me mp to the 5/3 times mass to the minus 1/3. Okay, so this is a mass-radius relationship for white dwarfs. It tells you that the radius of a white dwarf actually gets smaller as you make a more massive white dwarf. And that's a little counterintuitive, but that's one of the special features of white dwarfs. They get smaller, the more massive they get. And it's basically just a direct result of Heisenberg's uncertainty principle. So if we actually plug in these numbers here, account for all the factors of 2, you get a radius that's basically the radius of the Earth times the mass of the white dwarf in units of solar mass to the minus 1/3. So the typical size is basically Earth radius. More massive white dwarfs get smaller. We found white dwarfs all the way basically down to the size of the moon. Those are the most massive ones that we found. Ilaria has found some of those, as well as a few other people in this room. Okay, so what happens if we make the white dwarf more and more massive? Well, more and more massive means these momenta are getting larger and larger and larger. And eventually, it's going to correspond to a speed that approaches the speed of light. Okay, so the velocity will no longer just be momentum divided by mass. So in that case, we'll do the relativistic limit. Okay, so you can use this exact same equation, but now the pressure is basically going to be the number density times the momentum times the speed of light. Okay, so you can work through the exact same algebra, and this works out to h bar c over mass of the proton to the 4/3 m to the 4/3 over r to the 4th. Okay, so we're going to again equate that to the pressure you need to hold up the white dwarf. This time the factors of r cancel exactly. So you just have an equation for the mass, which is h bar c over g, mass of proton to 4/3. To the 3/2. It's just a bunch of fundamental constants. Okay, and when you calculate this is roughly 1.4 times the mass of the sun. This is the famous mass called the Chandrasekhar mass. So this is about the most massive of a white dwarf you can build up. If you make it any more massive, the electrons physically can't move fast enough to exert enough pressure to hold up the star, so the star is going to collapse. And all kinds of interesting fun and fireworks happen when the star collapses, which I'll get into a little if we have time. Okay, any questions on this? Yeah, there's no temperature. Doesn't appear. So that's one of the interesting things about white dwarfs is basically their state, their equilibrium doesn't depend on temperature. It's almost independent of temperature. And that's a special property of this degeneracy pressure, that the pressure is basically independent of temperature. So I'll talk about what happens when the temperature increases, because you do still have other effects like nuclear burning that can start to happen. But the basic equilibrium is almost independent of temperature. Okay. So one of the interesting things about white dwarfs, because they're so dense, is you get interactions between atoms that you wouldn't get otherwise. And specifically the atoms, it's one of the only times inside of stars when you actually get atomic interactions that are so strong that you build the nuclei into a lattice. Right? You basically get van der Waals forces that allow the nuclei to form into a lattice, so you start freezing the white dwarf. So you can calculate when that happens. So by the way, the ions are not degenerate. They have larger momenta because they have larger masses, so they're not degenerate. They basically have a thermal distribution. So you can calculate the Coulomb interaction, you know, the energy scale of attractive forces between ions due to van der Waals forces. It's basically the charge of an ion squared divided by the separation. I'll use delta X again. Okay, so this is basically charge squared. I'm going to put in the same expression for delta X. Goes like rho to the 1/3. Okay, so what we want to compare this attractive energy scale to is just the thermal energy scale of the ions. Okay, which is basically just kBT. So I'm going to divide this by kBT. And now this is an important ratio that we call the Coulomb parameter, gamma. And turns out this is roughly 100 for a temperature of 10 to the 7 Kelvin to the -1 and a density of 10 to the 7, which is pretty typical for the interior of a white dwarf. Okay, so what this tells us is that this attractive energy starts becoming very important at sufficiently low temperatures. White dwarfs typically start with a internal temperature of 10 to the 8, a few times 10 to the 8. But over time, they cool off. They radiate energy. The ions cool off. Once the temperature decreases to about 10 to the 7 Kelvin, this gamma increases above about 100, and that's when it turns out you basically start forming crystals at the center of the white dwarf. This happens preferentially at the center of the white dwarf because the density is highest there. Turns out the interior of the white dwarf is almost isothermal because those degenerate electrons are really good at conducting energy.
So that's all at equilibrium?
Sorry?
Is that at equilibrium?
Is what in equilibrium?
All this thermodynamic equilibrium?
Yes, so the ions are basically in thermodynamic equilibrium.
How do we know that?
Physics.
That's an easy answer.
Well, the time scale for interactions is very, very short. Actually, I'm going to calculate that in just a second. Whereas the time scale for cooling is millions or billions of years. So you're usually extremely close to thermodynamic equilibrium inside of stars.
Is there a 3D structure to the crystal? I mean, does it vary from the surface?
I'm sure there is. I don't know much about the details of the crystal structures that you actually form. I'll say one thing about the crystals that you form, which is that when you start crystallizing, so here's my white dwarf, you start crystallizing right at the center, and the crystals that you form, it turns out, are preferentially rich in oxygen relative to carbon. So what that means is as you start crystallizing, you start removing some of the oxygen, and the material around the crystal is now a little bit more carbon-rich than the surrounding material. And the carbon atoms, turns out that they're slightly less dense than oxygen. And so what this means is that the density of this uncrystallized carbon-rich material is now less than kind of the background white dwarf density. And so you actually form blobs of buoyant sea-rich material that now start to rise up through the white dwarf. So in other words, you get compositional convection, and then you have blobs of kind of normal abundance material that start falling down. So you drive convection around the crystalline core of this white dwarf, and that allows you to have fun things like magnetic dynamos that start operating. And how fast do they rotate? So what's fun about white dwarfs is they're basically the same size as the Earth, and they also rotate at about the same rate as the Earth, typically. Some of them rotate at periods of seconds. Most of them rotate at a period of about a day. And this physics is extremely similar to what happens at the core of the Earth, where you start building a crystalline iron core. You have less dense material that's left behind that buoyantly rises up. And so you have a dynamo in the Earth's core as well. We know that makes the Earth's magnetic field, so there's a lot of discussion in this conference about how this can build magnetic fields in white dwarfs, how that depends on the rotation rate, things like that. Sorry?
How do you know this? Shift in the spectra that we
yeah, so we do see magnetic fields in the spectrum, which maybe I'll talk about at the end. So we know that something like 10, 20% of white dwarfs have strong magnetic fields at their surfaces. This is happening in the core. We think those magnetic fields can start to poke out, but some of that physics, there's a lot of uncertainties in exactly that evolution.
Can I ask
Yeah.
a really stupid question? I must have missed something. How many of these white dwarfs are near us in the cosmos?
They're all over the place. They're almost as common as kind of ordinary stars, a little bit less common because the stars that have managed to form white dwarfs had to have come from stars about the mass of the sun or higher. So there are billions of white dwarfs in the galaxy. Does anybody know the exact number? There's a lot. So they tend to be almost as close as ordinary stars. They're very, very common. The problem is they're really dim, right? They're about 100th the size of other stars, but with similar temperatures. So their luminosity is about 10,000 times less, or 1,000 times less. So we can't see them very far.
What do you mean their dynamics? I mean, they're very heavy, right?
So they're about the mass of the sun, a little bit less or a little bit more. So they orbit through the galaxy very similar to other stars. You know, there's space is a vacuum, so it doesn't really matter how heavy the star is, it just orbits. Okay. Another fun thing that happens inside of white dwarfs that's this little... Oh yeah. But not just randomly. They probably only collide if they were already in a binary system. Because they're so small, it's very rare for stars to actually just collide in space. They usually have to be in a cluster or in a binary system, a triple system. Okay. So another fun thing that happens inside of white dwarfs is that there's sedimentation processes that actually affect their chemical structure. The heavier atoms tend to sink to the bottom of a white dwarf. So This physics is quite complicated. Lars knows it very well. He's had students work on this for their PhDs. I'm going to brush almost all that physics under the rug and just tell you that the order of magnitude for how fast an element sinks is about the gravity, the gravitational acceleration, times the collision time between interactions. So you could think of, you have a bunch of ions bouncing around, and every once in a while they'll come close enough to collide, and that happens on a certain time scale, which I'll calculate in just a second. The longer that is, so the less frequent those interactions, the faster they can sink down. You can think of the ions as they're playing Plinko and Price is Right, and they're bouncing all over the place. And they can, on average, they sink, but it takes a long time because they're bouncing all over the place. Yeah?
You said collide in quotes, like there's some ambiguity about whether or not there's like a hard collision or there's some interaction that's collision-like. Is there something interesting in there?
Yeah, so what happens, so a collision, remember these are charged ions, so they don't physically touch, they start repelling each other due to their electric charge. So we can calculate where that happens. So let's determine the cross-section for that interaction. So it's basically when the electric charge divided by the separation between those ions. I'll call this A. So when that separation is small enough that the electric repulsion between those ions is roughly equal to their thermal energy, that basically determines how close they have to get in order to collide. Okay, so you can calculate this cross-section for interaction, which is basically that size squared. And so that's basically Z E squared over KBT squared. Okay, so that's about that's how big an ion looks to another ion. Okay, so their collision time is basically the number density of the ions times the cross-section times the velocity. Okay, so you can calculate what this collision time is if you know the number density. And their velocity, like I said, they're basically moving thermally. So, yeah.
Did you not say that this was a dense gas?
It's a what?
Is it a dense gas?
Oh yeah, very dense.
So why is there not the distribution function?
There are. Yes, I'm not doing any of that. I'm just doing order of magnitude. If you want to do this exactly, it gets very complicated distribution function. Yeah, yeah, and there's electrons flying around here in here. There's screening. There's all kinds of other effects that make this actually much more complicated. Yeah, but this is the order of magnitude.
So you use kinetic theory?
You could ask Lars.
In the outer parts, you can use kinetic theory. In the core, you have to use more of the dense liquid.
Okay.
Yeah.
And it's corrected by quantum mechanics?
So those effects aren't very important for the ions. There's just the sea of electrons in the background. You can think of that as a sea of uniform charge. Okay, so let's plug in a couple numbers. So it turns out that for typical densities inside of stars, which are of order a gram per centimeter cubed for the sun, temperatures of 10 to the 7 Kelvin. This gives you a collision size of about 10 to the minus 10 centimeters. Okay, and so it turns out that this collision time is kind of order 10 to the minus 11 seconds. So in other words, the ions hit each other a lot. Okay, so that means if you plug in the numbers for something like the sun, you get a diffusion speed of something like 10 to the minus 7 centimeters per second. Okay, so a diffusion time for the sun would basically be the radius of the sun divided by this velocity. Okay, and that's something like 3 times 10 to the 10 years. So 30 billion years, that's a little bit longer than the age of the universe. So in the sun, this process isn't very important. It does happen a little bit, and we've actually measured that in helioseismology, but it takes a long time. It's a small effect. In white dwarfs, in the atmosphere of a white dwarf, or kind of near the surface, it turns out that there's some region where this density is also about 1 gram per centimeter cubed, similar temperature. So you get a similar cross-section inside of a white dwarf, similar collision time. But in white dwarfs, they're 100 times smaller, so the gravity is 10,000 times bigger. Okay, so for a white dwarf, this diffusion speed is more like 10 to the minus 3 centimeters per second. And the radius is smaller now, again by a factor of 100. So the time it takes these elements to sink is, well, I'll put down a number here, 3 times 10 to the 4 years. Okay, now that's a very short time scale compared to the cooling age of the white dwarf or the age of the universe. Now, this time scale is a very strong function of density. So basically what this means is the collisions are very infrequent at the surface of a white dwarf. So these diffusion times are large. And so near the surface of a white dwarf, the heavy elements sink very quickly. And so they sink below the photosphere of the white dwarf, and we can't see them anymore. Deep inside of the white dwarf, these timescales become much longer again, because the ions are colliding more frequently. But it tells you that, at least near the surface of a white dwarf, all the heavy elements tend to sink down. So physically, what you actually get is you get a very stratified structure. So, I don't know. I explain that.
Well, the gradient temperature can counteract.
Yes, so there are temperature gradients,
Yeah.
and those come into the actual diffusion equation. Yeah. The thing that is especially important that I didn't really discuss is the ions are heavier, so they always sink a little bit into the star. That sets up an electric field. And so what really matters is basically your charge per unit mass. That's what determines whether or not you can sink. And so it's the elements with a high mass per unit charge. Those are the ones that sink. So I'll talk about that a little bit. So basically the structure you get is you get this big carbon and oxygen core. Carbon and oxygen have almost the same, they do have exactly the same charge per unit mass, so they don't sink very much relative to each other. Helium actually also has the same charge per unit mass, but first of all, the white dwarf forms with the helium shell. Second of all, there are, I think, small effects of diffusion that amplify, that cause the helium to rise up above the carbon and oxygen. But this is especially true for hydrogen because it has less mass per unit charge. And so the hydrogen all rises to the surface of the white dwarf. So most white dwarfs, when you look at them, you just see hydrogen in their spectrum. There's no traces of anything else. Now it turns out that something like, was it 20% of white dwarfs don't have hydrogen? They actually burned all their hydrogen and you only see helium at the surface. And then there's a small fraction of white dwarfs where you don't see hydrogen or helium. And those probably came from more exotic evolutionary channels, and people are very interested in this conference at discussing the origins of all those weird kinds of white dwarfs. But most of them you just see hydrogen. So there's a couple other interesting elements. One is neon-22. Okay, neon-22 has 2 extra neutrons compared to things like carbon and oxygen. It has 2 more neutrons than protons. So it has a larger mass per unit charge. So it tends to sink. It turns out there's a fair amount, was it 1% of the mass, roughly, is neon-22. A similar fraction, maybe a little bit less, iron-56, also has some extra neutrons. So these elements will sink down, and so one of the things that might happen inside of a white dwarf is you actually form a little core of neon 22 or iron 56 right at the center. And that can especially have interesting consequences when you think about then when the crystallization process starts happening. There can be very interesting multi-phase effects where, depending on exactly which elements you put into your crystal and lattice, you can get very interesting effects in the material that's left behind, and you can have distillation processes where you change the composition of material. You can have basically the lighter material, like I said before, tends to rise up. Sometimes you could actually make a crystal that's lighter than the liquid, so then the crystal would rise up, kind of the opposite of like rain falling down in the Earth's atmosphere. So all kinds of interesting things can happen here at the center. Yeah. Well, not directly, but one of the things we're trying to do is actually use the observations that we do have to infer what happens. So let me give you an example. So I made this plot of luminosity versus temperature. So I said, here's the main sequence, here's the red giants, here's the white dwarfs. And I said there's this little branch that sticks off the side called the Q branch. So one of the things that we have been discussing, and there's a lot of discussion in the literature, is about how white dwarfs, they basically move down this way as they cool. But you can imagine a bunch of white dwarfs cooling, and it turns out that this line corresponds roughly to when the core starts crystallizing in the white dwarf. And so if that releases enough energy, that can keep the white dwarf warm. So you can imagine a white dwarf moving down, it's cooling, but then the core starts crystallizing, you get an extra source of heat, especially if the crystallization can cause things like neon to sediment out. You might be able to actually prevent the white dwarf from cooling anymore, so it might just sit there for a long time. So that means if you look at all the stars in the Milky Way, you'd see a bunch that are sitting on this line because they take a long time to cool through that line. And so there's a lot of discussion about if that's what's causing this feature that we see. So by making these observations, we can start to get a handle on all the complicated physics that's happening at the center of the white dwarf. Okay. We can also do things like find planets or the disrupted remnants of planets around white dwarfs. The main way we do this is by measuring their spectra. Actually, a lot of what we do in stellar astrophysics is measure the spectrum of a star. So we plot the flux as a function of wavelength. So most white dwarfs, you'll see some feature like this, where these big broad absorption lines correspond to absorption lines, the Balmer lines. These are absorption lines caused by hydrogen. So H alpha, this is at 656 nanometers. And then there's this Balmer decrement down here at about 360 nanometers. So if the white dwarf just has hydrogen at its surface, you just see these absorption lines. That's what we see in most white dwarfs. But sometimes we see other elements. So there are things like iron lines. Maybe Boris can help me out with the exact frequencies of all these different absorption lines. We see calcium lines here in the blue. There are things like magnesium lines somewhere out here, sodium, and a few other elements. So we see those in something like, was it 20% of white dwarfs? Yeah, Boris says that's right. So what that means is that these white dwarfs must be accreting these elements because, like I said, the heavier elements tend to sink down on very short time scales, maybe 1,000 years, 1,000,000 years, something like that, depending on the white dwarf.
What do you call them absorption lines? You don't do the absorption measurement, but you do the emission lines.
So they're absorption lines because we see less light at those frequencies. Yeah. So this is the flux.
So where's the light coming from that is being absorbed?
So the light's coming from the star. It's just diffusing out of the star. But then, magnesium in the atmosphere of the star absorbs light at very specific frequencies corresponding to electron energy transitions. And so you can measure that in the spectrum, and then you can infer that there's magnesium in the atmosphere of the star.
You cannot exploit other wavelengths like infrared or something.
Oh yeah, you can.
It's just too messed up in terms of too many transitions.
No, people use every wavelength of light that they can possibly use to do these kinds of studies. But most of the telescopes, especially the ones on the Earth, are looking in optical, right? Because all the UV is absorbed by the atmosphere. A lot of the infrared is as well.
Where's the light coming from? The light, same question.
So it's just thermal energy diffusing out of the white dwarf. Yep, it's just thermal energy, and because white dwarfs have temperatures similar to the sun or hotter, that thermal energy is radiating it. Sorry? Yeah, so it's roughly a black body spectrum, but then there's these absorption lines that on top of that. Yep. Yeah, so the peak of this black body can be very different. This would be a fairly cool white dwarf. Some of them, the peak is way in the ultraviolet, so you just see a line rising up. So yeah, the spectra are very diverse, and you can learn a lot from them. So we see these elements, and it turns out the main elements that we see are things like iron, oxygen, silicon, and magnesium. These, by mass, these are the most numerous elements other than hydrogen in the atmospheres of a white dwarf. Does anybody recognize these elements? What kind of material has these elements? Yeah, rocks. It's basically the same abundance ratios as bulk Earth. So like a third oxygen, a third iron, a third other stuff. So we know these white dwarfs are accreting rocky material, which we think are the disrupted remnants of either planets like the Earth or asteroid belts, things like that. But these abundances they're different from, say, comets. Comets have more water and carbon, I think.
So you said they came from elsewhere. There was the fusion made them elsewhere.
The 8 subplanets.
Yeah, so there's a lot of research by a lot of people in this room as to where exactly these elements are coming from. The basic idea is that you have your white dwarf, and then it has an asteroid belt that actually gets disrupted because the star loses mass when it forms the white dwarf. So all those asteroids start scattering with each other. Mostly they start scattering off of other planets. So eventually they might get sent onto a very high eccentricity orbit that passes close to the white dwarf. The tidal force then shreds that asteroid, and so it forms some disk of dust that then basically gradually accretes onto the white dwarf. And we know that these white dwarfs have to be continually accreting because if they stopped accreting, these heavy elements would quickly settle out of the atmosphere and you wouldn't see them. So this is actually quite a common phenomenon, and it allows us to probe the planets that were around these stars when they were like the sun.
So this is kind of the shell around what you see there. These absorption spectra come not from the stuff that's around the white dwarf.
It comes actually from the surface of the white dwarf. In a few cases, you see things like infrared excesses that are coming from the disk itself. Yeah. Okay, so I promised I would talk about some fireworks. So let's talk a little bit about when white dwarfs collide, what happens when they increase above this crucial mass, the Chandrasekhar mass. Okay, so thus far I haven't talked about nuclear burning. So let's get into it now. So, turns out that once the temperature inside of a white dwarf gets bigger than about 500 million Kelvin, then you get hot enough for carbon burning. And I think the first reaction, or one of the most important reactions that starts happening, is you fuse two carbon into a neon, and a helium. And this spits out about 5 mega electron volts of energy. Okay, so that happens if the white dwarf heats up enough. So what's really interesting about white dwarfs is that typically these nuclear energy generation rates, they are proportional to temperature to some very large power, like temperature to the 40th or something like that. So what this means is once you start nuclear burning, you increase the temperature, and then that accelerates the nuclear reaction rates. And so what a star like the sun does when that happens is typically in a star like the sun that's supported by gas pressure, the pressure is proportional to the temperature, right, for an ideal gas. That's always true. And so if the pressure increases, then what happens is actually the star expands, and that causes it to cool off a little bit, just from adiabatic expansion. So that's how a normal star regulates its temperature, and it finds an equilibrium. In a white dwarf, we said that the pressure was independent of the temperature inside of the white dwarf. So once this nuclear reaction starts, the temperature goes up, the reaction rate accelerates, and it's a runaway process. And so you get essentially a big nuclear bomb. And this happens because of the degenerate nature, the fact that the pressure is independent of the temperature. So that's a very special thing about white dwarfs. So this process accelerates. And once the temperature is larger than about 3 times 10 to the 9 Kelvin, you reach a state called nuclear statistical equilibrium. So basically what this means is the temperature is high enough that all the nuclear reactions reach some equilibrium. So it's very similar to a chemical system where, you know, there's always a reaction and a reverse reaction, and you find some equilibrium based on the pressure and temperature and all of that. Same thing happens with nuclear physics, as long as your temperature is large enough that all the nuclear reaction rates occur on a short time scale. So that happens once your temperature gets larger than about 3 billion Kelvin. So as an analogy, if you heat up a mixture of hydrogen and oxygen, you all can probably tell me what the product of that chemical reaction is. Right, so it's just H2O. Okay, and you know that that's potentially explosive chemical reaction. So basically the same thing happens, but with nuclear reactions. Once this nuclear runaway happens. So, of course, there's a lot of elements involved here, but the most important ones are basically helium nuclei, and heavier ones like carbon-12 is basically just 3 helium nuclei stuck together. So you could just think of it as all the different combinations of helium. And the most important one in this context is 56 nickel. That's basically just 14 helium particles stuck together. And 56 nickel, it turns out, has the lowest binding energy. It's the lowest energy state that the nucleons can reach inside of an atom. So that means just like you tend to burn H2O and O2 exothermically into H2O, you tend to burn helium exothermically into nickel when this nuclear runaway happens. And so you fuse maybe half the mass of the star into pure nickel. And that all happens basically in about a second or so. So the white dwarf might just sit there for billions of years, and then something causes a spark. As long as you get a spark to ignite this nuclear reaction, it'll run away, and you'll release a lot of energy. So white dwarfs are basically just floating powder kegs, just waiting for something to ignite them and make them explode. So how much energy do you actually release? So every time you do this, it's something like 100 mega electron volts. Okay, so that's each reaction. Okay, so the total energy released is basically the number of nickel-56 atoms that you make times 100 MeV. And if you just calculate the number of nickel atoms inside of a white dwarf of about 1 solar mass, it turns out that the energy that you get here is about 10 to the 51 ergs, which is so ergs is, the CGS units for energy. To translate that maybe to a more familiar number, this is about 10 to the 28 megatons of TNT. So that's a really big nuclear bomb, the biggest nuclear bombs in the universe. And this energy scale is a very famous energy scale in stellar astrophysics, because basically all the supernovae we see are at about this energy scale, and it's for this reason. So it turns out, actually, there is kind of a more subtle reason. It turns out that the gravitational binding energy of a white dwarf, which is basically gm squared divided by the radius, it turns out that that is maybe like 3 times 10 to the 50 ergs. It just so happens that this is a little bit less than the amount of energy you release during this thermonuclear detonation. But what this means, this energy scale is bigger, so it's enough energy basically to totally blow up the white dwarf. So what happens is you release this amount of energy in about a second, and it's enough energy you just thermally now have enough energy to blow the whole white dwarf up. So that's called a type 1a supernova. Those are the most common supernova that we observe. They're quite bright, they last a long time, they're easy to find. You can see them at gigaparsec distances, so you can actually use them to measure the expansion of the universe. And this is the famous way that the acceleration of the expansion of the universe was measured, was by finding these supernovae, these explosions, and measuring their brightness. So, this is what happens when you start the burning, but what actually causes the burning to start? This is an open question in stellar astrophysics. It's one of the biggest outstanding questions, and something that we talk about at this program. So basically, like I said, you just need a spark. So what is the physics that causes that spark? So there's a lot of ideas. The classic way that you do this is that you accrete just from another star. And once the mass of the white dwarf is greater than that crucial mass, the Chandrasekhar mass, I said that's when the white dwarf can't support itself anymore, and so it starts to collapse. But when it starts to collapse, it also heats up. And so then you can start this nuclear runaway. So that's the classic idea. People have studied that in excruciating detail. We still don't totally understand it because it depends on the propagation of the flame that starts with the burning. This is was the classic idea of how you make these explosions. It's a bit disfavored now for a variety of reasons, although there's still a lot of debate about this. So this is called the single degenerate channel. The other way you can do this is called the double degenerate channel, which basically just means that instead of accreting from a normal star, you accrete from another degenerate star, aka another white dwarf. So you merge two white dwarfs together, and either that gets them above the Chandrasekhar mass, or the merger process itself is violent and heats up the material enough to start nuclear burning. Let's see, Ken isn't here today, but there's also variations of this, like the double detonation scenario, which maybe is the most interesting one. So in that scenario, you have your carbon oxygen in your core. The helium around it is also degenerate, and so instead of starting with the carbon burning, you can actually also detonate the helium, and that basically causes a shock wave that then wraps around the white dwarf, and it turns out you get this converging shock wave, which converges coherently at the center of the white dwarf, And that heats up the center of it enough to then start carbon burning, so you blow up the rest of the white dwarf. So that's basically, that's basically the same concept as a lot of nuclear bombs. That's how the Fat Man worked. So this is just a very large-scale nuclear device. So there's various ways you can ignite the helium at the surface of a white dwarf. And so that's one of the things we're talking about, how to ignite those ignitions. And specifically, we want to know, depending on how you ignite this, it might change what the supernova looks like. And so that's going to be really important if we want to use those supernovae to measure properties like the expansion of the universe. Not to mention just the astrophysics is cool by itself. So I was going to do gravitational waves, but are we out of time?
Yeah, let's take questions. Let's do it.
Okay, let's do questions. Thanks.
Are there mechanisms to form white dwarfs that are not stellar evolution?
I think all the mechanisms are basically stellar evolution that I'm aware of. I didn't talk much about helium core white dwarfs. So there are low mass white dwarfs that are just helium. These, instead of being so normal carbon oxygen white dwarf is about 0.6 solar masses. These are usually more like 0.3 solar masses. These don't form by themselves in the age of the universe, so you need a binary interaction between two stars that strips off the hydrogen off of a star, an evolved star like the sun. Before it starts helium burning, then you're left with a helium white dwarf. In principle, if you could take a ball of hydrogen and cool it off as it contracts so that it never ignites hydrogen burning, you could make a hydrogen white dwarf. But I don't think we know of any process that allows that to happen at this kind of mass scale. Brown dwarfs are basically those balls of hydrogen, but in that case, they just never get massive enough to ignite hydrogen. But in principle, you could do it at this mass scale if you could cool them before they start burning hydrogen. But we don't know of any process that can do that.
Would any of the open questions that you've discussed lead to a recalibration of this expansion of the universe idea? Do you understand what I mean?
Yeah, so basically, the way we measure the expansion of the universe is there's this very well-known correlation called the Phillips relation that basically relates the width of the duration of a supernova to its absolute brightness. And so then by measuring the duration of a supernova, you know its absolute brightness, so you know how far away it was. And then if you also measure the redshift, that basically tells you, it's another way of measuring how far away it is. And so that tells you actually how the universe has been expanding over the time interval that the light traveled. So if something modifies that relation, maybe because the mechanism is different at large distances compared to short distances, then that would modify cosmology and our measurement of the expansion of the universe.
Is that likely, would you say? Or
I think
pretty confident in the physics?
I think that depends on who you ask. But I think it's certainly possible that it modifies things at a few percent level. So very small levels. And there is a slight tension, basically, between different measurements of the expansion of the universe based on either the supernovae or things like looking at the cosmic microwave background. So a lot of people want to know, to a few percent precision, if those relationships are good, and that may change based on the physics.
Great. All right, well, thank you so much, Jim.